My name is Joe Colas. We have a lot of things. And in half an hour, we have 15 demonstrations to show you. So it's going to be pretty rapid fire. Next out is Kyle, and he's going to be showing us our gravity gun. And this takes a little bit of setup. So during this time, I'd like to point out that everyone in the club, at least I think everyone, will be wearing one of these shirts, and it says, "Everyone knows equals MC squared, even English majors." And this is a quote from one of our professors. We have a board of professor quotes, and this was chosen the #1 for the shirt. And what's really cool about this shirt is the back of it has a written out proof for E equals MC squared. So the very last line is E equals MC squared, which is really cool. At least for physics majors. So, Kyle, you ready?
I'm kind of.
Okay. Well, you're not.
Give me a moment.
Okay. Okay, so what we're going to do is show you a show in 3 parts. And the first part will all have to do with how things interact physically. So like gravity and energy and momentum. You'll hear these words a lot. What were you going to say?
I'm ready.
Okay. One thing I want to tell you is after this you're going to see a momentum thing. Momentum is something that uses mass and velocity. So something with high mass or something with high velocity has a lot of momentum. So we'll see that later. I'll let Kyle take over.
Okay. Here we have a dart gun. It's pretty simple. It's spring loaded. We have a magnet which holds a target up here. Now when the dart will pass through this light sensor, the target falls, and we have this wire in here. So when I shoot, the target's going to fall. Now where do you think I should shoot to hit the target? So I can hit the target. So we're going to go with at the target. So I have a laser sight. This is here I'm pointing roughly. Not quite right, but.
That went a lot faster than I thought it would. That went a lot faster than I thought it would. Damn it. That went a lot faster than I thought it would. Jeez. Already at fucking 30 minutes.
Now what happens here is when I shoot, target drops.
Shoot at it straight on.
I am. At least I'm trying. When the projectile comes out of the gun, the forward and backwards motion of the particle towards the target isn't affected by gravity, but the up-down is. But the up-down motion of gravity, the change, also affects the target in the same way. So when the target and the projectile will fall at the same amount, so when the dart reaches the cork board, it will hit the target.
Yay!
Okay, so
Physics
what we
to
learned
say.
here is all things fall at the same rate. So if you had a rifle and you were going to blast a rifle, at what angle would you have to blast it so that it would fall at the same rate of a bullet that you just dropped? Does anyone know? Like, what angle would you shoot it at? Any ideas? That's right. The mind has it right. You shoot it straight across. You shoot it parallel to the ground. If you shot a bullet up at all, it would take a lot of time to go up and down. But if you shoot it straight across, it'll land on the ground the same time that you would drop a regular bullet from your hand. So what I was telling you about momentum uses mass and velocity is an idea that Sean here is going to continue with our air tracks. So Sean, you can take it away.
Yep, we have our air track here. We're going to place these 2 parts here. We can consider them called cars if you want. They don't have any wheels. But we have a little firecracker in here, and we're going to add some energy to this. But because we started with no momentum, we have to end with no momentum.
Oh, can I interrupt just real quick? Because I forgot to say this. I need to make a loud noise. What's the word? Warning, I guess.
It's not very loud.
So
It's a little firecracker.
this one's going to make a little firecracker. Later on in the show, we're going to have a lot bigger explosion. I always plug my ears. I advise you to do as well. But that's later in the show.
Alright, we're going to turn this vacuum on here just so there's very little friction so these can move pretty easily. As you can see, we have minimal friction, so we'll go ahead and start. And they come back together, and they stop. It's like magic. And that's confidence.
So the lighter one went faster and the heavier one went slower. Does anyone know why? Anyone want to take a gander? Because what? Oh, you're so smart. So when you incorporate mass and velocity, you get momentum from that. So they actually had the same amount of momentum. Because the one was lighter, it had to go faster in order to conserve momentum, what we call conservation of momentum. So we're going to go on to conservation of energy, which is a topic Nate will discuss.
All right, who here likes to swing? All right, how do you go higher on a swing? You have to push. But if you don't push at all, you stay the same height. That's potential energy right there. You can only have so much. You swing down, it becomes kinetic, goes back up to potential. You can't cause any more without a push. So I'm risking my nose for this experiment. Imagine the bowling ball is a swing. It won't hit me in the face because no one gave it any more energy. And that's the idea behind potential energy and conservation of energy. To show it another way is my other friend, Nate.
Okay, everybody. This is called Newton's cradle. Some of you may have seen this before. Basically, I have one ball that I'll move, and it'll hit and it'll move this ball. This is conservation of momentum and energy. To make sure everybody knows, these are all the same weight. Ta-da! Is there any suggestions for how many balls that I should move this time?
3.
3? Ta-da!
4.
Do 4 at a time?
Yeah.
How about I do 4 on one side and 2 on the other?
Yeah.
Oh, that. And that. But as a better example, do 2 and 1. 2 and 1 works better. But as a better example, I have my friends bringing out something you can all see. These are normal bowling balls, weighing about each 15 pounds. I have now successfully done that. We will now move on.
So conservation of energy tells us things don't just spontaneously go faster or slower. You gotta put energy into them. Like the pendulum swinging, it doesn't automatically go high for whatever reason. No, you have to push in order for it to go higher. Well, this also works for things that are spinning around. If you are, I don't know, if you're a figure skater, you don't just spontaneously start spinning. You have to put energy into that. Well, to further explain this, we have Blake with his lovely assistant. Oh, man! You know, every single time in practice I mess up their names, and then the real thing comes, and then I mess up their names again. This is Andy with his lovely assistant, Blake. All right, I'll let you guys take over.
Alright, so to start off, I'm going to have Blake hold his arms out with weights in his arms. So I'm going to give him a little bit of a stick. Not too much at first. And now watch as he brings his arms in. whole lot faster. And this is due to conservation of angular momentum, which you talked about linear momentum already, which is the relationship between mass and velocity. And this works with his distribution of weight and the rate at which he spins. So when he holds it, actually we're going to do this again, a little bit faster. See how well you can hold it. Let's get Blake. Now we're going to do something a little bit different. I'm going to have him hold that tire, and we're going to speed it up. Now he's just standing there, not spinning, with the wheel spinning. Now if he turns it over, so the wheel is spinning the other way, he starts spinning. So when he flips it over and the wheel is spinning the other direction, in order for the overall spin to stay the same, he has to start spinning the other way. And this is angular momentum. This will be out here after the show for you to play with if you want to.
So we talked about momentum and energy and angular momentum. Well, now we're going to completely change topics and talk about electricity, which is a fun topic. But briefly on angular momentum, it's a really important physics property because it's what keeps you on your bike when you're biking down the road. The wheels don't want to change direction at all when they're spinning. When they're stopped, you know, your bike will topple over. But since they don't want to change their direction, that's what keeps you upright on your bike. Now, I want to try something here just because it sounds fun. When Derek turns this on and you see what it does, could everyone go, ooh? I think that would be very cool. Let's try it out.
Should I just turn it on?
Oh, no. Take over.
Oh, okay. So, what I have here is a machine called Jacob's Ladder. And what it does is it will make a beam of plasma across these two metal prongs. And the reason it does that is it will cause a voltage difference between the left one and the right one. And this is a lot like in a thunderstorm, where you have clouds and the ground, and you see lightning. All that's doing is it's equalizing the difference of charge. Now this will do the same, except we'll maintain this difference of charge all the way through each of them. And we'll see what happens.
Yeah.
Ready? Okay, now the reason that it's moving up is because this beam of plasma, or lightning, is really hot. It's superheated. And as we've probably, most of us have heard, heat rises. So that's why it's going up to the top of the two prongs. Are there any questions about this? Yeah.
How much positive and negative do you use?
Sorry?
How much voltage do you use to negative?
Okay. The one in the front? Yeah, it's a positive and negative charge on each side. And in the back, actually, I'm not sure what the voltage is on this.
I don't know.
I don't see your finger and find out.
I would not want to do that. Unless, well, no, I wouldn't. I can look it up and after the show I can let you know. So, yep, that is Jacob's Ladder.
Question, is that indicative of the fact that lightning goes from the ground up?
Actually, I think that, yeah. Kind of. It depends on which charges are where. It's the electrons, the negative charge that move. So, it depends on whether the negative charge is positive.
Well, to take over from Derek, same idea of electricity and magnetism. We have Blake with the Van der Graaf and the Tesla coil. Are you ready, Blake? All right.
All right. Who knows what this thing is? Well, besides Van Gogh. Who knows what it does?
Hey, you hit it.
wipers down here that, work like you rub your butt on a couch. It does that sort of thing.
There's just a bunch of little butts.
And it takes the current, or the charges, and distributes them up here on this conducting sphere, semi-sphere. And they'll collect on the outside of this. And so I turn this on, my magic wand here is actually connected back into the ground. So once this gets warmed up, you can kind of hear it cracking, and then the lights. I'm going to use my finger. Ridiculous. But if I touch it, I can stick my hand on it. No big deal. But I don't want to take the wand off before my hand off because then I'll get shot. Alright, so I'm sure you've all seen where you've got some girl and she comes up here and she puts her hand on here and her hair starts standing up. Well, this is our girl's head. As you can see, she's a little worse for wear. Now it's, I guess it's more of a balancing act. Okay, so we have our girl, and she comes up here, she sticks her hand on here, and these charges that were in here are going to start going into her head. And then they're going to want to go out as far away from each other because they want to repel, like two magnetic poles do. They'll try to repel each other, so when I turn this on, her hair stands up. Now, once again, this is grounded, and these charges want to go down to the ground, and so they're following my magic wand. Yoda would be proud. Charge goes away, no more repulsion, so they go back down, back up, down, up, down, up, down. All right, so one last demonstration with this sphere of death. And, well, flying saucer demonstration. Once again, the charges are going to collect up here because these are metal pie plates. Sadly, no pie, or go outside. And once again, the charges are going to be up here, and they're not going to want to be next to each other. So I turn this on.
I didn't mean to actually make contact.
Now, does anybody know what this crazy contraption is, besides the fact we called it a testicle? Who knows what a testicle does, besides you three and whoever else has been here? Anybody know what a testicle does?
Electricity.
Electricity. Anybody know who Nikola Tesla is? Everybody see the movie The Prestige? Hugh Jackman? The crazy scientist with the cloning machine? That's what this is, only the cloning was made up. You can't really clone people with this. His was just much bigger than this one. So in the movie, okay, it works. In the movie, he had a giant field where he had a bunch of bulbs in it, and he turned on the machine, and all the bulbs glue. They turned on. Glue. And so you turn it on, and with the lights, there are no wires connected to my bulb. Over here, it starts lighting up. If I turn it out here, the whole bulb goes out. Now, unlike Ghostbusters, it is okay to turn off the screen. And besides making a lot of noise, what are some applications you think of a machine like this? Guitar Hero? Well, that isn't quite how wireless cords work. This machine, instead of wires to your house, you can have one of these in your front yard and it would beam electricity into your house. And the thing is as scary as it looks, it's pretty safe. I mean, unless you stick your finger between here.
you'll be just fine. I've been standing here for a while. I've done a couple shows. I'm just fine. I'm more worse from wear from maybe spinning me around in circles than I am from handling this. The amazing thing is for as neat as this invention is, we don't really know how it works. So if I say, if someone asks you how does the Tesla coil work, you say magic. Because it works. That's the magic part. And I can't think of anything else to say.
The next demonstration is my favorite one. It's very cool. You guys don't want to leave right now. It's really the best one we got. The next one. Oh, actually, that's a valid. Okay, so they are going to the. Actually, I won't tell you because I don't want any of you guys to leave either. But what they're about to do, you can do after the show. So, what Luke is taking out here is a gigantic version of our Van de Graaff machine, and it has a bit of history to it, which Luke will explain. Well, similar physics. Anyway, I'll let you take charge.
If you'd like to arrange that for me, please. All right. I'm not a doctor. I am not a mental patient. Well, I'm common. To some degree, this could be an institution for, never mind. All right, so, you've seen plenty of things that were shooting sparks, right? Yes, boring little light shows. All right. So we have this, and this is a little odd that it's in the physics department because it's actually a medical apparatus. See, in the 1920s, it was used for treatment of things such as headache. Here's the little book we've got of it. Headache as well as constipation. We haven't tested either. After the show, though, there might be some headaches, and if you're willing to volunteer, we might take your photo with this on. But the idea is, at least for one of the setups for treatment, you would sit on a table, and the table would be connected to the machine on one side. You've got two electrodes over there. The other electrode would be attached to this, and suspended over your head. Now, this machine can reach up to 50,000 volts of potential difference, which is probably larger than the household wire rates to now, right? Now, this differs from our other machine in a certain way. It's so large that we can actually break glass instead of air. I'm not certain you can see that very well. That's a pane of glass, about 8 thick, that we broke with this machine. Now, we had a much thicker one, but after the last show, while carting around the back room, we knocked it off.
That's a good thing for you.
Because we found this, which we're going to try. But, because we know it works with one this thin, we're going to try it first. So, I believe the machine is set up. Excellent. Igor will be cranking. So all we've got here is, we connected the electrode to the wrong side, Igor. Yes. This is that one. All right. So, okay, complete circuit. All right. So I got a wire attached to that one, running to this metal plate. Here we've got a wire coming up from the metal plate to this pole. I'll stick the plate of glass I just showed you on top of it. I'm trying to make a nice seal. We've got some goo on there so it connects. It's goo. It's sticky. You want to play with it? All right. So the thin plate. Yes. All right. Now attempt to electrocute me, Igor. You can hear it cracking a little bit. And if you look, you can actually see it going through the glass as opposed to around it. Go ahead and keep cracking. See, there it shoots under. Go over. Good. All right, go ahead and stop it. So, push yourself. Did you contact? Okay. Good. Would you care wiping this off and showing them that this glass has in fact broken? I'll take the large glass, which we're going to try to break. That's my ability. All right.
Right?
Yes.
We haven't done one this big before, so not in a while.
Well, we haven't. Other people claim so.
Oh, it's trying.
It's, oh, it just goes under.
We're going under.
Yeah, but
That one did.
That one didn't.
are you serious? It looks like it's going under me. It's like going around.
No.
We'll try to reset it in 1 second. There's no guarantee this will work anyway. But we just like to try things, you know, offhand when people are around.
It makes us look good, yeah.
That's still going around.
Yeah, it's still going around.
Well, sorry. We apparently get a bigger piece of glass. Anyway. So, up to 50,000 volts. And didn't break this one, unfortunately. However, it won't be available after the show for you to play with. The reasons may be obvious. We think it's some interesting scarring pattern.
Burned it a little bit there.
But that's not as cool as breaking stuff. All right.
Okay.
Thank you, Luke. All right.
Can you spin that with the lights on? Is there something moving in that cabinet?
Oh, yeah.
Oh yeah, there's 4 plates in there.
There's quite a few plates back there actually spinning.
It's called a Holtz machine. For people who want to do research. You're volunteering. Really? I'm gonna have to get the waiver. Did you go and fetch that from downstairs? I think it's the universal certificate clause.
So what is the damage effect that's actually you did use that for medical purposes?
For
Well, okay, imagine a normal electric shock when somebody rubs their feet across the ground.
Yeah.
That's what, a couple hundred volts, probably, with very full current.
all depends on your distance, but yeah, I mean, if the earlier you went and saw Jacob's ladder, right? The gap at the bottom of that thing is what, 1 or 2 centimeters?
Yeah, something like that.
And that's about 1,000 volts. And this is 50,000. And we had a safety cage around that one.
It would not be pleasant at all.
This one we're not smart enough to put a safety cage around it.
With the safety cage around the safety one. That makes sense. Okay, so we have 2 more topics on electricity and magnetism, or 2 more demos, I should say. And you're going to hear a big word thrown around, induction. And basically, when you hear it, all it means is you're making a magnetic field from electricity. So when electricity flows in a circle, it makes a magnetic field that goes through the circle like that. So like if you plug in your vacuum, and there's a little cord wrapped up, that doesn't actually make a magnet because you have electricity flowing in opposite directions around that wrapping of cords. So it actually forms 2 magnets that cancel each other. But if you have a wire, everything in the wire flowing the same direction, you'll make a magnetic field. And this is called induction. And to continue induction, here's Derek.
So what I have here is an aluminum rod, or pipe, I guess it's hollow, as you can see. And as we saw earlier with the monkey guns, well, we would expect 2 things to follow at the same rate of speed, right? Follow as fast as the other one. Now one of these is a magnet, and one of them isn't, and as we can see, neither one is really attracted to the aluminum. So what I'm going to do is I'm going to drop each one through the pipe, and we'll see what happens. First, I'll drop the non-magnet. This is just a piece of metal through the pipe, and see how fast it goes. And it fell through pretty fast, right? Now, this is a magnet. I'm going to drop it here. And it's taking its time. Now the reason it's taking its time is that as it travels, it's a charged particle, charged item, and it's moving through this pipe, and it's inducing a magnetic field. And the pipe wants to counteract that because in nature systems don't want to change. So counteracting this, the pipe is causing another magnetic field which is pushing against or resisting the fall of the magnet. So that's an example of induction. I was going to ask if there are any questions about it. Yeah.
If that was glass tubes, would they fall through at the same rate?
Yes, it would. It has to do, so since this is aluminum, it's, and also if it were slitted, it has to be a solid tube, because otherwise a current that's caused wouldn't complete, the circuit wouldn't be complete. So it needs a constant current to go through there. So even if I had a slip through here, in theory, they would both fall relatively quickly. So, and glass wouldn't slow it down at all. Any others? All right.
So again, electricity flowing in a circle makes a magnet. This is called induction. To continue induction, we have Josh.
Okay, what I have here is an induction coil, and that comprises of power supply down here. And this is a coil of wire with an iron core, which acts as a magnet when I turn on the power. And because that is a magnet, in the exact same way Derek's pole acts as a magnet to oppose the other magnet, this ring is turned into a magnet by the electromagnet. So it's the exact same principle. There's a force acting on it, but this magnet is quite a bit more powerful than the one Derek was using. So you can expect quite a bit larger force from this. So we will see if we turn it on. And so we get a force, it goes up. And also in the same way Derek's demo worked, the force is caused by a current going around this circle. And so electricity flows better when something's cold. You know that. And so what I'm going to do next is do it with a ring that has already been cooled down to liquid nitrogen. So we'll see what happens. This one is very, very, very cold. It does that. Did I try to catch it? Okay. Oh, no.
Okay, we saved the best to last. The next three demonstrations are all pretty cool. But before we go on to them, I want to make sure you all learned something. So we're going to play a little game. It's called Explain the Physics in 4 words. So you only get 4 words. Okay, so the first one, the gravity gun, you shoot at the target. Okay, can someone explain the physics behind this in 4 words? Think about it. Okay, anyone? No, not you. Come on, somebody. Very good.
Who said magical?
We're talking the gravity gun. Why is it that the dart hits? Why is it that the dart hits the target even though they both fell? In 4 words, anybody? Falls the same speed. Perfect. Genius. That's very good. Okay, let's do one more. Angular momentum. Anyone can explain the physics of how that worked in 4 words?
Angular momentum is conserved.
Angular momentum is conserved. That sounds good. Now, technically, I heard that one last time, so I don't know if you were listening in there, but yeah, that's right. So, when they pull in, it goes faster to conserve angular momentum. Well, we are going to venture into a new topic, low temperature physics, and to take over is Luke.
So you may remember me from that demo that didn't work well, or you know, basically from anything where someone talks a lot and you're just going, why is he talking? So I have here a couple doers of liquid nitrogen. Now, I believe you just saw the induction ring, right? Nods, general nods. Thank you. All right. So one of the rings he cooled down in liquid nitrogen, right? Now, he went and explained that that made the current go faster and so forth. But how cold is liquid nitrogen? Anyone know?
0 degrees.
That's pretty good, yeah. Negative 321 Fahrenheit. All right. So comparing that to, say, our tropical temperatures right now, you probably don't get a good idea of that. However, you know, you can freeze water all the time, right? Make ice. Well, something this cold, we can freeze other things. And as physicists, that's what we think of, you know. Hey, I can freeze water. Can I do it to Rex's chew toy? So let's stick it in there. That'll take a little bit. In the meantime, my lab assistant shall attempt to inflate this balloon. Now, after the show, we're going to have Marshall. He was doing that in the back for minutes. Alright, after the show, we'll have marshmallows and grapes that we're freezing with nitrogen. The grapes won't be frozen all through. But you can just eat them. Properly, don't care. Alright. Well, Blake is using an air compressor, which we call the lead of the club. I would like to show you this rose I bought. It's pretty cool. It broke pretty well. Can't do better. Now, it's just a rose. We just froze it. What? You did great. Did you inflate it?
Yes.
All right. So, sounds like a good idea. Let's get the ball out. Why don't we play anymore? So it'll warm up quickly. Now this balloon, we can jam it in here. And I can talk and mutter and whine, which I do anyway. I mean, it's the same thing he does over there. Now, you'll notice it appears to be deflating. Does anyone know why? Someone talk about temperature already? Ah, yes, you and that.
The molecules moving slower and liquefying.
Okay, moving slower. That's good. Now, what's that mean? They're moving slower. Well, they don't push as hard. If they're moving slower, they're not hitting things as hard. You can try that outside with neighbors and so forth. All right, so this will take a little while for this one to completely deflate. However, in the interest of saving time, we've taken one. And as it's pretty well deflated, it won't stay deflated for long. But it's going to pop on its belly. Or it's going to pop a little hole in it and deflate. The last one is leading through the hole. I don't like that balloon. We don't have another try for this. We can do this. Well, I don't have another try for this, so you can't pick on me. However, after the show, we're really doing Meissner effect, which is where we put a magnet on top of a superconductor and it levitates. So if you want to come up here and see that, because it's a very small demonstration. And as I said, we'll have ice cream, or not ice cream, well, grapes and marshmallows. Ice cream we never do we?
I don't think we ever do much ice cream.
All right, I'm done.
So temperature, why are cold things cold? Does anyone know on the molecular level why cold things are cold?
The molecules have less energy.
Molecules have less energy, right? Yeah, and what gives something energy? Heat? Yeah, this is on the right topic. So when little molecules are vibrating, when they're moving along, the faster something goes, the more kinetic energy it has. Kinetic just means energy for moving. So on the microscopic level, when things are bouncing around a lot, that means very high temperature. When they're not bouncing around very much, that's very low temperature. So what we saw was the liquid nitrogen, very low temperature, things weren't bouncing around at all. And, well, it's a nice segue into the next topic, which I'll have Jason explain.
Hello, everybody. So we usually have our chemistry major do this, but she just graduated and went on to Berkeley, so we're really proud of her. This balloon here is full of hydrogen. Anybody have any fun uses for hydrogen? Very good. You smart earlier too, wasn't it? Oh, yes, but is that a good idea? No. It's a very famous balloon. Let me do a little example.
You may want to plug your ears.
You might want to plug your ears for this one. So that was good. So what we did there was the hydrogen mixed with the oxygen in the air. Got a nice boom. So what I did is I went ahead and concentrated some oxygen, got it back in a bottle back there, put it in this balloon. Let's see what we do if we have a balloon full of just oxygen. That's boring. So, oxygen itself doesn't burn, but it helps things burn. So, in this one here, I put hydrogen, if you can see it, and oxygen together. Does anybody know any good uses of those two together? Water. Water. And that's my favorite one. Veishea uses it for rocket fuel. So we're gonna leave you a countdown on this one too. Please cover your ears for this one.
So what happened on the molecular level right up there? Anyone want to take a guess? Yes? Anybody? Exploded. So what? Exploded? Exploded, I guess that's a word. So what did the individual molecules do there? Does anyone know? Chemical reaction. They, yes? Well, I only heard the first part of that, but you said energy. So, yeah, so suddenly they started vibrating a lot more, and this was powered by the chemical reaction. So it was very, very hot, and hotness is essentially the amount of energy molecules have, and that energy just means how fast they're going. So hot things are vibrating really fast. So this is our final demonstration, and one of our very best ones, and it has to do with waves.
Yep.
Do you wish to take over, Sean?
Actually need a hand to go. Somebody needs to hold that, please. But basically what we're doing here is we're going to run some sound through this tube. And sound, as you know, is a wave. And as waves travel, they have peaks and troughs just like this here. And what we're going to do is set up a pattern of two waves going back and forth. And you're going to start to see a pattern like that in the flames because it's going to change the pressure of the gas inside the tube. And as that pressure changes, it's going to allow the gas to move faster, slower, in and out of the tube, and cause the flames to go. So we're going to go ahead and run a sound loop here with a certain frequency just to go ahead and demonstrate that. I'm going to turn up the gas a little bit just to get everything going. Down a little bit so we can get a good pattern once we actually turn it on. So, let's see if we can get a good pattern going. This one's okay, but it's a little low. Let's move up a little bit. Maybe less gas. There. Alright, we probably need to. Alright, here we go. We got a little bit of one going now. This is what we would call the, what? This is like 7, maybe 8. So you can count the peaks. I don't know how well you can see them, but it looks like there's 1, 2, 3, 4, 7 peaks. The last one's here. It's kind of weak, but so that'd be the 7th harmonic. So if we lower the frequency, we're gonna move the interference patterns around. And there's what, 2nd, 3rd. And we can just dial through all of them if we really wanted to. Then we go back and forth. And we have some music to play for you. Alright, that's waves. Couldn't blow up a balloon? That's don't want to ruin the speaker. I think we're good.
So a few things for you. First of all, a number of our demonstrations we'll have up here for you to see. There's the Meissner effect, which will take just a little bit of assembly, maybe just 5 minutes, but it's very cool. It has to do with levitation and magnets, very cool. And we also, there's a planetarium showing at 4 and 5 o'clock today, and you can follow the science and physics to get down there. All right, can we have everyone come out? Thank you for coming. Again, you can stick around. We'll have a few demonstrations after. Oh yeah, and if anyone would like to ride the upper draft, we'll have it out in the hallway.
Yeah, that was way too long.